store today, Matthias Bussonnier from UC Berkeley, will start out. Then we'll have Suhas Somnath from Oak Ridge National Lab talking in more depth about a use case that he's been involved in for Jupyter Notebooks. And finally, Shreyas Cholia from NERSC will be talking about how NERSC has deployed Jupyter on their HPC systems. We do want this webinar to be interactive, as it notes there. We encourage questions, but because we have so many people on the webinar, we would ask people to put those questions either in the chat box in the WebEx tool itself, or go to the Google Doc that's noted there with the bit.ly link and list them there. And we will stop periodically and go through those questions that come in. We will make the slides and a recording of this webinar available in a couple different places. The Exascale Project archives these, and so does the IDEAS Productivity Project. And you'll receive email when those archives are available in case you want to let some of your friends know about it. And finally, I would ask you to please give us feedback. That last link on the slide is a very short survey that gives you an opportunity to provide feedback about this webinar or the webinar series in general, including other topics that you might like to hear about. And we're very happy to get your input. We would like this to be as useful as possible. With that said, I will get out of the way and we'll let Matthias start out.
Thank you very much, David. Let me see if I can switch to my slide. Okay. Can you see correctly? And do you hear me?
Yes, we do.
Okay, great. So hi, so I'm Matthias. I'm originally a biophysicist, and I've been a core developer of IPython and Jupyter since 2012. Before it was actually Jupyter. I'm also a co-founder and steering council member, so I know a lot about what's happening in Jupyter these days, and I'm one of the older developer here that I spend most time on Jupyter. And I'm currently a postdoctoral scholar at BILS, and I'm working, like, my full-time postdoc role is to work on Jupyter. So as David said, this webinar will be in 3 parts. I will talk for about 20 minutes, 25 minutes with time for questions, and then we have Suhas and Shreyas that show 2 15-minute use cases. For my part, I will roughly divide the talk in four parts. How do we went from IPython to Jupyter? What is Jupyter? Why is Jupyter popular? And some Jupyter usage, but we have more information from the other speaker for that. So everything started almost 15 years ago, more than 15 years ago, where basically Fernando Perez, who wrote IPython during his PhD. So basically, why did he write IPython? He basically had a bunch of Perl make files, C and C++ files, and had to basically run a lot of commands to do things, and discover Python that basically could replace and make the glue between all of that. Except Python doesn't have a really good REPL. So REPL is read-eval print loop. It's a command line interface you use to interact with Python at the command line. And so he wrote IPython, a couple of 100-line script that was basically having integration with some caching, some prompt numbering, and gnplot integration, because he was doing a lot of outputting. And IPython grew a lot for about 10 years, until around 2011, when the first second interface that was basically network enabled, as we'll see later, appeared. You may know it as the Qt console, where basically you had the Qt interface that was able to execute Python code, but also display images in line, which is quite convenient when you're iterating instead of having floating windows everywhere. And in 2012, the birth of the current notebook. If you heard about the Jupyter notebook, we'll describe what it is a bit later. One thing that you might want to know is that the current notebook that we're using is actually the 6 prototype. So there are a lot of failed attempts before that. And basically, we made IPython network enabled. And all of that was made possible in around 2012 because the web technologies became mature enough to be able to run a powerful app in the browser. That's, for example, WebSockets, that allows servers to push things to clients that were not really available until 2012, and also the rise of JavaScript JIT engines that made JavaScript relatively fast in the browser. 1 year later, around 2013, the core IPython team I was part of at the time sat down with the Julia team. So Julia is a language from MIT that you may have heard of. And in about a week, we managed to update some of the IPython assumptions that the code was Python. And the Julia folks wrote a kernel. And so by 2013, the IPython notebook at the time was able to not only run Python, but run Julia with the toggle of a checkbox. Around 2014, because a lot of people were complaining, like, why do you have to install IPython to run Julia, or why do you have to run IPython to run R? We decided to rename all of the Python agnostic part of Jupyter to Jupyter. And now we're in 2018, and there is several million users. And last week, JupyterLab was released. That's a quick history to understand how we went from a simple a few hundred lines script to a multi-million user project. So the question often we have is, what is Jupyter? And it's highly dependent on the people you talk to. When you talk to an average user who just started with Jupyter and is not really aware of all the pieces, the main thing they talk about when they say Jupyter is notebook. And even the notebook is a highly overloaded term. When you go down to the project, what it mainly is a web server and a web app, which is able to load IPOENV files that are JSON that contain code, narrative with math and results. And you can see an example here on the screenshot with the Lorentz attractor, and you can see that a single document can have both code, result, and narrative. And the particularity of this kind of document is that it's attached to a remote kernel that is doing computation. And the process that is doing computation is what in the Jupyter lingua we called kernel. We'll discuss later what a kernel can be. And the other thing that because we are here in the notebook using a web browser as a front end, the results you're displaying can be of several types. You can have static results, like, for example, just text, a string that is, for example, displayed by print, or you can have interactive content, basically completely JavaScript client-side, dynamic, interactive panning and zooming, for example, of graphs. We can have dynamic code, which basically is interactive in the browser, but will be able to call back into the kernel to do some computation. So here, for example, in the screenshot, you see sliders, and if you were to move a slider, that would trigger a computation in the kernel that would solve the Lorentz attractor for different value of the parameters and show the new result back. Jupyter is highly focused on exploratory programming. IPython was designed for exploratory programming as a REPL and grew popular because of that. And Fernando Perez, who created IPython, coined that in a nice sentence in 2013. In IPython, we have weaponized the tab key, which really expresses how people are using IPython and now Jupyter. Basically, you are trying to figure out a problem, which is inside to do something. So you will, for example, load data, and then you write in your preference code your object dot, and then you press tab to see all the methods that you can call. Then you call this method on an object that returns a result, and this result updates your prior on what you understood from the data, and then you iterate over that. So Jupyter is also an open organization with open governance. If you've been contributing for some time, we'll probably ask you if you want to be part of the governance and try to direct where Jupyter is heading. And we are funded by grants and donations, as well as collaboration like Anaconda, who is contributing developer time instead of money to the project. So NumFocus is a non-profit organization that manages everything for us, and we're funded by these days the more Sloan and Helmsley Foundation. More technically, Jupyter is a set of protocol and formats. We reduce the n frontend and n backend problem to the m frontend plus n backend. Before Jupyter, when you wanted to execute code in a specific editor or a specific front-end, you would have to write a specific plugin for this editor and this language to be able to communicate. By having a standard protocol, which is open, free, and relatively simple, basically you just have to adapt to this protocol and write this protocol, and then suddenly you have all the other side of the equation free for you. And especially front-end people rarely want to write back-end code and vice versa, which means that if you are a front-end person who would like something nice, you can just focus on writing your front-end, and you get all your language. And if you're a language geek that doesn't know anything about design or layouts, you can focus on manipulating bytes for the protocol, and then you get all this way of editing live code. And so why do we focus on something relatively simple and open? Because we are also target toward science and interactive use case. We know that most people that are using Jupyter are not computer scientists, and we want something to be relatively easy to write, or for future people who replace us to understand what we did. And so we also see a lot in the document format about science and interactive use case. That's one of the reasons the results are embedded in the documents, which is sometimes a critique we have, like why is it complex JSON? That, for example, help to not have copy-paste mistakes. If you already have given talks with results from experiments, you often have forgotten to update the specific figures. And here, by having everything embedded, when you see a result, you're pretty much certain that it comes from the code which is next to it. Jupyter also scales easily, both in the number of CPUs that you use, but also in time. Like you can use Jupyter from education to HPC, which means that you don't have to relearn other tools. And we see more and more people using Jupyter early on. So with all of that, we have a really large ecosystem. Everything which is in bold here is developed by the core team, and everything which is not in bold is community maintained. And you see that we have a couple of front ends maintained by the core team, but we have, for example, plugin for Vim, Emacs, Visual Studio Code, Atom Interact, etc. Even an iPad app called Juno, so you can literally access HPC from your iPad at home. We developed kernel. The core team maintains the IPython kernel, but we have a bunch of kernels, and I want to highlight a couple of them. Especially, you have, for example, Fortran kernel and a C++ kernel, which means that you can run in Jupyter interactive C and C++ that is able to display rich objects, and a number of building blocks. If you really don't like what we're offering, you can rewrite your own, which means that you can completely use Jupyter without using any of the things the core team is actually writing. And so, speaking of front ends, last week was JupyterLab release. And so, what is JupyterLab? It's a new interface which is completely compatible with all the other ones, which extend what the current notebook can do with a text editor, shell, etc. And the question we have is it an IDE? And yes, if by you mean IDE, yes, you mean interactive. The specific feature of JupyterLab is that any file format that JupyterLab can open, it can be backed by the kernel. So if you open a Markdown file or a PY file or anything else, you can use select with an option and say attach that to a Python kernel and a Julia kernel, and then run code directly in this document. On the questions on the document we see here, I heard that JupyterLab is gonna release version 1.0. It seems that JupyterLab and Jupyter are going to converge to one. So Jupyter is, as I said, a large project, mostly protocol and everything. There is JupyterLab, which will be the official way of running notebooks that we offer. We still have the classic notebook that you're all using. The classic notebook will be retiring in a couple of years. We'll maintain both for a certain amount of time. But so far, everything that you can do with a classic notebook, you can do with JupyterLab. And as JupyterLab is a much more sane code base, it's going to be easier to extend, and probably will get more features and more stability than what the classic notebook offers. And it's ready now if you want to use it. The internal API may still change a bit, but you're free to start installing it and use it. So popularity, if we look at the Google Trends for a search of Jupyter and Jupyter Notebook, and look at the number of notebooks that are on GitHub that we try to estimate, we see that there's been an exponential growth since 2014 when we decided to rename part of the project to Jupyter. So why that? We think that one of the reasons is that we based a lot of our decision on interactivity, because coding is not the end goal of most of our users. They often just want to get insight into something. They're not always proficient in coding, and a simple single tool with a friendly interface really helps, especially if you're new to computing. When you tell someone that they need to learn how to use SSH key, SSH for cluster, and submit things, they get scared. The fact that you have a persisting kernel state that allows to iterate on a specific part of your computation. Like if you have to run a large simulation and then make graphs, you might not be familiar with how to serialize data on disk and reload them. What you can do is run a lot of computation and then just loop in the notebook on what is interesting for you. And the notebook interface gives a great interactivity in between the REPL and the script. You can iterate on a specific cell really quickly, but everything you did before and want to do after is really linear, and so you can edit that relatively easily. Plus, the intermixing with narrative allow you to really explain what you're doing with math if you like math, and you can either explain the code or the result you have, which is great for sharing. The separation of state of the documents in the front end that you're editing and in the back end where the code is running is also important. It's quite robust to crash. If your code is crashing, you still have the document which is in your front end, and you still have your results that are visible. So you can try to figure out what went wrong. This also means that because some state is in the document, you can save the document, which is a single JSON file, and send to someone. And even if you run that on thousands of cores, the end results can be read and viewed by others. So you don't have to write the different reports to explain what you've done. And it's also relatively trustworthy because you know when you see some graph in the notebook that they're coming from the code which is just next to it. So you don't have copy-paste issue between documents. There are a few cons, especially for newcomers. Understanding that the document state and the kernel state are different can be challenging. So there is always this question of when do I have to rerun everything, which is a bit still a bit hard to teach. And of course, the notebook format is not flat text, so it's not always as widespread as other formats. So some people cannot edit the file without installing plugins or installing Jupyter. Another reason is the fact that it is network enabled and web-based. We don't need to forget that usually people get attracted by really good design, and fancy colors and nice looking things attract a lot of users. Here is a comment that we got from a user last week when we released JupyterLab. The fact that you can have dynamic library and visualization like D3 in the front end is really attractive, and you can have several users, either novice and power users or users with different expertise working on the same notebook. Which means that, for example, you can have someone who is really good at numerical method writing code, someone else writing visualization, and if you're not native English, for example, you can have someone who is good at prose that will write the different narrative. There can be also a relatively seamless transition from your local laptop to HPC in a really nice configured environment. You can play with code on your machine with a notebook, and once your notebook is almost ready, you can head for the menu and just say, well, restart this computation on the cluster, and suddenly have thousands of cores available for you. And in an organization context, if your IT have installed JupyterHub, then you can have completely zero installation. So you're just arriving to a national lab, for example. It hooks into the authentication system. As long as you have a web browser, you can head to the right URL, you enter your credentials, or you're even already logged in. And then you have access to a powerful computing environment. So I just want to talk a tiny bit about JupyterHub. JupyterHub is our way of having multi-user deployment. So we don't have yet real-time collaboration. It was a plan, but unfortunately it was going to use Google Drive, a real-time API that was retired last December. So even if it's working, we can't use it. And one of the large advantage of JupyterHub is that each user can get their own process version of configuration. Unlike many other applications, when you deploy an application at IT level, you usually will have a single version of the application for everyone. Here it gives a relatively large flexibility. So if you want to have some users with a really specific use case, you just need to tweak that for them. And they can, for example, be on bleeding edge on a custom patch version without affecting other users. One other thing that I want to mention is that JupyterHub is not limited to running Jupyter. You can, for example, behind the JupyterHub, run RStudio or OpenRefine or some other things like that. So just going to look at one question or two in the document. There are questions about JupyterLab and CoCalc evolve together and have them merge. So CoCalc was also known as SageMath Cloud and is a for-profit company. We allow people to use Jupyter for whatever they like. We are in discussion. We often have feedback from the people from CoCalc, and we try to integrate as best as we can. But we have different requirements because they have clients, and we try to do things open source. So we don't go at the same speed. And in JupyterLab, is there an option to have Matplotlib pop up in the separate windows within the JupyterLab interface? That probably has to be implemented. You were welcome to create a pull request. It might need some update to the protocol. JupyterLab was just released. So obviously, there are still a lot of things that can be done better. The challenge often is that we need to support that for many languages, and so it takes time to really design things the correct way, and implementing the correct way take a long time. So now let's go into Jupyter for HPC. How can you use Jupyter in HPC? So you could, for example, run batch jobs. You have the possibility to run notebook headless using one of the building blocks we provide, which is called NV-convert. And you can even parameterize notebook, for example, to have reports on different events. If you're studying, for example, an astronomy value stars, and then if you see that a star is behaving weirdly, you can reopen this report and rerun it by changing just the way, just the pieces that looks strange. But that's now not how most people use Jupyter on HPC. Basically, what people want is an interactive cluster. The way you do that is asking IT to run a hub. Then on a logging node or a head node, you run a notebook server. And this notebook server can spawn kernels that will do computation either on a head node, if you're just playing around, or on a fast queue, depending on your setup. And when you really want to do some computations, then you actually restart the kernel and all the workers, for example, Dask or MPI, on your cluster. And suddenly, you basically just move from a small computation environment to a really large computation environment without having to SSH completely check that your environment works. And so let's see some example of that. We'll see three, LIGO, Pangeo, and Cern Swan. So you've probably seen that a year ago, 2 years ago, the LIGO interferometer discovered, confirmed the existence of gravitational waves. And so some of the event analysis is done with Jupyter. So they have a notebook that basically allow you to go through to the data and fit the theory to what have been recorded by the interferometers. And they package all of that into a repository. They will provide a subset of the data and put that online. And using a project called Binder, you can, for free, run that on Google Cloud. So I'm just going to click here. So that's going to take a couple of seconds, and you will directly have access to a live notebook instance when you can rerun a log analysis. Here are two except of the graphs you can see. So if you see the white chirp on the second graph, which is blue here, so that's that energy per frequency domain through time, and this is basically the sound of two black holes colliding. And if everything was fast enough, now probably a lot of you have access to the link here. You can try it by yourself, and you can rerun the analysis and literally listen to two black holes colliding and change the parameter of the fit by yourself in a few minutes. And it's a really nice way to show that you actually have access to a trustworthy, reproducible artifact of detecting gravitational waves. And all of that is both run on really large data and small sample that can be rerun by anyone with access to a browser. There is also Pangeo, the Pangeo project, which is on GitHub. It's an effort from the Atmosphere, Ocean, and Land Climate Science to have a single set of tools that are readily available online, using recent technology to be able to simply do science. So it uses really recent technology like DASC, which is heavily developed, and Jupyter. Also things like Kubernetes, Google Cloud, and will create machine on the fly. I highly recommend reading one of my blog posts on pangeo.github.io. There is also a video showing how you can do that. And here, what you can see in this screenshot is an analysis of the weather temperature, I think, on the United States. So that's on the left side. And on the right side, what you can see is the DASC cluster working, like the function run by the DASC cluster through time. And you can see in red at the beginning that the DASC cluster is just initializing and loading data, then doing nothing. And then suddenly, when the user executes something, you have hundreds of tasks that get spawned, communicate data to each other, and return the final result, which is a map you see on the left side. So here you have a perfect example of interactive cluster, which is not only interactive in the sense that you iterate your data, but that the cluster is created on the fly when the user log in on Google Cloud. But you could imagine providing that and hooking that into another kind of machine. And I wanted also to show a tiny bit about Cern Swan, which is a shared platform data analysis for the Cern. If you have a Cern account, it directly sync with your home directory, and it's zero install. They actually provide a gallery, and you basically browse your gallery, find an example that looks great, whether it's in C++ or Python. And then you will just click on this visualization, and it will fork things for you and allow you to run this data analysis on your specific data set, and then you can basically modify and get insight into your data. It's really impressive that you have underlying the browser C++ REPL to do particle physics. I'm going to be out of time, so I'm going to say that if you want to learn more, we have JupyterCon at the end of August. You still have a few days to make a proposal, and I'm going to read a few questions maybe while we are changing speakers. So I'm going to stop sharing, if I figure out how to do that, and answer a question. I'm going to, we now have Suha, I think, that will take the next talk. Have you considered using some of the spider feature in JupyterLab? Well, yes, but it needs to be implemented. It's like the same question before. It takes quite some time to implement. I am an author maintainer of the Coarray Fortran kernel. Are there API changes that will require kernel maintainers to update their kernels that currently run your notebook to allow them to run in JupyterLab? So no, you don't need to change anything. JupyterLab does not change the protocol. JupyterLab does not change the format. JupyterHub is just a nicer interface. We strive to have the protocol and the format as stable as possible. And if you change format, you will get notified relatively early, and we will provide mechanisms to automatically adapt for other front-end or other kernels from one version of the protocol to another. So you don't need to change anything. If you are missing something because you think that there are some things in the protocol that you need, feel free to send this to us, and we will at some point, not this year but next year, start to think about updates to the protocol and really clearly think about how we want to move things forward. You mentioned in the slide that Jupyter could be run interactively on the cluster. Could you send a link to the corresponding documentation? The problem is that the documentation is a bit everywhere because there are really a lot of moving pieces. There is not a single documentation on how to do that because there are many ways of doing it. But we are going to have a meeting to talk about some of that with Shreyas. I don't know when. We can try to loop you in if you put your email in the document. And I think that's it for questions.
Thank you very much. Shreyas, do you want to go ahead and start projecting your screen?
I think we have Suhas on next.
Oh, is it Suhas? I'm sorry.
Can everybody hear me now?
We can hear you. Thank you.
Okay, awesome. So hi everyone, this is Suhas Somnath. I'll be talking to you about one of the examples similar to the ones that Matthias talked about. This is specifically going to be about how Jupyter has been instrumental in transforming both the in-house as well as the support for and training for external users who come to the Institute for Functional Imaging Materials, where I was a postdoctoral researcher until June of last year. So the concept of the feedback loop between series simulations and experiments has been elusive for many fields. Numerical simulations, as you probably are all familiar, are very popular on the big computing machines. However, while they're not at the same scale just yet as simulations, analysis, processing, and visualization on experimental and observational science data is also growing quite rapidly. There are a handful of observational science research groups, such as the neutron facility that we have here at the SNS at ORNL, the nuclear sciences, the bioinformatics, etc., that have been generating vast amounts of data and are currently using the leadership facilities for their processing or understanding of the data. So now most of the remaining observational science groups might acknowledge the urgent need for the desire to get into big data and analytics, but may find it challenging to go from the signals that you get from instruments to the data that can be explored at scale on something interactive like Jupyter on HPC, for example. I'm going to take this specific example of the materials imaging community and show you that how even such relatively new and small fields can generate enough information-rich, structured observational data that can go hand in hand with the simulation data to complete the feedback loop. And also, obviously, I'll be talking to you about the important role that Jupyter has played in the transformation of this institute. So in order to show you how Jupyter, supported by a domain-specific Python package that we developed, has changed research at this institute, let me provide you a glimpse of the state of microscopy before I began work in this institute. Many of these observations are still true of many more scientific domains in general. And let me start off by saying that as with any experimental facility, this institute has numerous microscopes of different kinds, of which generate data of different sizes, different dimensionalities, going all the way from 2D images to 7D spectroscopic matrices, and each capable of different kinds of modalities of acquiring information from the samples and resulting in different kinds of data. One of the first observations that I made when I was there was that the data sizes in the observational sciences have recently exploded and are growing very rapidly regardless of the instrumentation that you pick. So clearly laptops and desktop PCs won't cut it anymore. Following the desire to understand more about the materials, we often want to correlate data coming from multiple instruments and modalities, and this becomes another challenge because each experimental mode and each instrument generates custom data or data in a custom file format, which is challenging to open up and explore. What's more is that the software provided the instrument is almost always simply incapable of doing the necessary analysis or visualization that's often necessary to generate the next a giant leap in science. Consequently, the analysis software for each of these modalities and instruments was being developed and separately by each group of people, and people were rewriting pretty much the same filtering or processing algorithms or analysis algorithms, and these are not being shared. And when people do share the analysis code, what we were noticing was that people ended up doing so by emailing each other snippets of code, which is far from ideal. And furthermore, there was a giant monolithic MATLAB GUI that was built specifically for user support. Now, I'll get to why that was not the ideal solution. Furthermore, even when somebody sends you some code, you may not be able to run it because you have an older version of MATLAB or you didn't pay for getting the MATLAB license. And these licenses are getting extremely expensive. Finally and importantly, DOE obviously, for DOE, neither the data nor analysis software was shared when reporting in a recent publication, and as a consequence, there was no guarantee that could be given for reproducibility. And this is a major problem if you're going to go forward in this era of open science. Clearly, there is a urgent need for a paradigm shift in the way one needs to think about data, software, reproducibility, the dissemination of knowledge that you acquire after completing a set of experiments. So at this point, I guess I can take some questions, and maybe I can stop at a later slide. But if there aren't any, I'm going to go ahead with the fact that so our goal was to eliminate any compromises in science due to the complication in the volumes of the data format and the program data analysis, the high performance computing, the communication, etc. Everybody wants to go straight from the signals from the instrument directly to interactive data exploration and instantaneous computation. However, to make that dream a reality, we need to start from the basics, and you need to fill in the gaps there. One of them is obviously an automated and standardized way to acquire data, and one solution that we found was LabVIEW software. Obviously, the bigger instrumentation facilities like the Neutron Sciences facility will have their own custom C++ software. But anyway, this is just an example. And the next step was, and this is very, very important, the development of a standardized data structure and a file format that can represent data that's all the way from 2D kilobyte-sized images to terabyte-sized 7D hyperspectral matrices. And then obviously there's the need for the common sense way of developing software as a community, which is a centralized hub or a repository, which is going to hold all the analysis and pre-processing routines. And finally, after all that, we can think about scaling to HPC and having the data at the point where it's ready for interactive visualization using something like Jupyter. So as I mentioned, we developed this custom and centralized software repository, and this one was called Microscopy. It was meant specifically for the scanning probe microscopy community, and it was built in such a way that it was built, maintained, and extended entirely by domain scientists. We chose Python because it's easy to use while having access to all these obscure libraries that you need to open files or analyze materials, data sciences or something. So, like I said, we used a standardized data format, which, regardless of which instrumentation you came from, you could speak the same language of data. And then, obviously, if you had a standardized way of representing your data, you could write one version of your filtering and your fitting algorithms and your decomposition, clustering, what have you. And finally, the final part of this package was what I'll be talking to you more about in detail, which is how we convey information, how we disseminate knowledge that we acquire, how each user disseminates knowledge after they come to the user facility, which is through the process of these interactive Jupyter notebooks. So as I mentioned to you before, the facility where I worked, the software situation was such that people were passing around scripts, as well as there was this custom, complicated, huge monolithic MATLAB GUI that was being given to users, and it required a software engineer for about 3 years to write the software. Obviously, it was not at all customizable, and every time a user came into the facility, they would not only require hours of instrument training to use the instruments and grab the measurements by themselves, but also they would require 2 to 3 hours of training of the software before they start analyzing their own data. And what's more, it was all written in MATLAB because that's what they thought was ideal in those days. And as a consequence of the expensive licenses, they were only deployed on 2 workstations. So people literally had to stand in a queue to analyze the data. And if you extrapolated how that would have gone, the situation would have been you either buy more workstations and deploy the software there, or keep it on the same offline desktops. So starting from 2016, when this microscopy package was developed and these Jupyter notebooks were developed on top of that, all of this transformed. So this complicated MATLAB GUI became a set of simple Jupyter notebooks that were written by the material scientists themselves, and that could be customized if necessary for each user. And after these things were deployed, the instructions were only given for operating the instrument, and there was no training time. The users didn't require any training for using these notebooks because they're so self-explanatory. And right now, they don't have to stand in a queue to analyze the data. They're all getting their own VMs, which are reasonably powerful, with all the Jupyter notebooks preloaded on the server, so they can just go ahead and analyze the data. And while in the previous case, nothing would have happened beyond those offline desktops, this institute is in the process of exploring JupyterHub, transitioning to JupyterHub, so the users don't even have to install the software on their own laptops. So the other place where Jupyter has truly transformed science, at least in that specific domain, is that as of 2017, they were aiming for publishing all new scientific journal papers with to be accompanied with a Jupyter notebook. There's one right here on the right, along with the data itself that was acquired. So you have data all the way from the raw measurement that is acquired from the instrument, all the way to the specific figures that were plotted or generated for the paper that's shown right here on the left. And this combination of this Python package and Jupyter has allowed us to disseminate knowledge that we acquired from numerous projects, and this is just a selection of some of them. And we've made tremendous advancements in being able to convey the information a lot more easily, and our users are substantially happier because of the fact that even though this is a notebook, these are interactive notebooks. So what they get are those nice widgets that they can use to slice and dice their multidimensional data and explore the data to their heart's content. So with this, I hope I've conveyed that if you think through this properly, you can indeed complete this discovery paradigm of the feedback loop between simulation and observation, so long as you have well-structured data and a software package that is there to back it up. And so I specifically talked about one institute, which was the Institute for Functional Imaging of Materials, which focused on scanning probe microscopy. I can see I can see the same paradigm being applied to other institutes in the lab and beyond. And Shreyas is going to be talking a little bit about this, but essentially each community would have their own package of choice that they would write in their own language, and you could have JupyterHub deployed on some sort of a cloud. And here in this case, we're using the Compute and Data Environment for Science, which is the CADES, and with JupyterHub deployed there, one could essentially service users and also in-house research and run these big computational jobs, like Matthias said, on the big leadership class computing facilities. And the OLCF is making progress in this regard, and these are being explored. But Shreyas will be talking a little bit more about this in the subsequent talk. With this, I'd like to thank the teams that have been instrumental in making all of this possible. With this, I'd like to take any questions that you might have. So, okay. Good question about
Share your screen so I can set up.
Yes, of course. Certainly. Just give me a second. I'm still sharing the screen. Okay. Stop sharing. All right. There you go. All right. So while Shreyas gets up, I'm just going to answer the handful of papers. A handful of questions that we have here. Has there been any discussion about DOIs for notebooks? Good question. We're actually packaging up we're doing a single DOI for the data and the notebooks for right now. We haven't specifically talked about having DOIs for the notebooks alone. As far as experimental data is concerned, you would need both in order for something to make sense. So potentially, if you did not require any data, or if you're not doing analytics on your data, then I suppose you could certainly have a DOI for a notebook. Who's pushing all papers to have notebooks? Yes, this is specifically the culture that's being set up in that particular institute. DOE is encouraging people to do this, to have for all papers to have to be essentially the science to be reproducible, and this is one way we think that we can accomplish it. Also, in that particular institute that I talked about, that this is the paradigm they're picking. These kids have JupyterHub deployed already. Yes, it does have JupyterHub deployed for a very specific group. There's a gentleman named Damien who's worked on this. Any cluster teams that already have Jupyter deployed for fully at the centers, I'm not entirely sure I can answer this at the moment. Maybe I'll think about it and answer this at a later point. All right, I guess Shreyas.
Yep. So I think that maybe that last answer is.
Yes.
I guess what I'm going to be talking about our JupyterHub deployment at NERSC is the short version of this talk. So maybe that answers part of that last question. So you guys can see my screen?
Yes.
Okay. All right, so I'm Shreyas Cholia, and along with Roland Thomas and Shane Cannon, we've been working on a JupyterHub deployment at NERSC, and this talk is primarily about that. So most of you are probably at least somewhat familiar with NERSC given the community, but we do have the Cori system. This slide might be a little bit old, but the point here is that we're trying to sort of set up this paradigm where Cori has both a HPC partition, which has KNL nodes, but also a data partition, which is focused on data-centric workloads and supports things like real-time queue, shifter, Jupyter, burst buffer, among other things. So we're really kind of looking at data users as first-class citizens on the Cori system. And as I talked about, Jupyter is sort of an important part of this strategy, and part of where this fits in, I mean, this is maybe somewhat of a repeat of some of the stuff Matthias and Suhas already talked about, but the idea is that Jupyter notebooks give you these kind of literate computing narratives where you have code and comments. You can reproduce your science, you can show your work, document your workflow, but then you can also have rich text and interactive plots and widgets all in there, which allows for this iterative exploration to arrive at insights. The other side of this is that Python also has a pretty central role at NERSC, and when we did our last survey, I think Python was by far the most popular language at NERSC. Not even necessarily as the code that runs the backend simulations, but some projects are using it for HPC. But a lot of projects, even if they're using other codes in HPC, they're actually wrapping some of this stuff in Python to script up their workflows or to perform the exploratory analyses before and after. And so this kind of led us to Jupyter and wanting to have something where we can deploy Python in a standard way for everyone. And JupyterHub kind of became the thing that we used to deploy that. So users running their own, we noticed that users were just starting to run their own notebook servers on our systems, which means that people are basically running a web service on there, and it started to make some of our security people uncomfortable. Plus, people were having their own environments, their own kernels, so dealing with tickets there was its own challenge. So JupyterHub became a way to centralize the deployment of notebooks at NERSC in a standard authenticated manner, and we could package up some standard kernels through Anaconda, and crucially, it gave people access to things like the underlying file systems, or the batch queue, or the network, or the databases. So as Matthias mentioned earlier, JupyterHub is really Jupyter as a service, and it is a service you can use to deploy notebooks on the cloud, or notebooks on a cluster. So the JupyterHub service manages user authentication, notebook deployment, web proxying, and then what it does under the covers is fires off a notebook per user. So the user logs in with their NERSC username and password, and they get their own notebook on a Cori login node. So to kind of give people a sense for how we got here, the first sort of requirement we wanted to deal with was just giving people access to data at NERSC and then having them be able to do what they need to do. So in this model, we basically had a Docker container that ran this JupyterHub web service, and it had the global file system mounted on there, and people would log in and get this notebook server processed, and they had access to the file system. And mostly this was for pre- and post-processing, but almost immediately it became very popular. OpenMSI, Lux, Metabolite Atlas, a bunch of projects started using this. However, there were some key things that were missing in this deployment. Among other things, the Lustre Scratch file system was not accessible here, and we didn't have access to the batch queues or the same Python environment as Cori, because this was its own little Docker container that things were running under. So step 2 was figuring out how to integrate this with the Cori system. And so what we ended up doing is deploying JupyterHub as a web server that lives outside of Cori, but it's then going out and spinning up these notebook server processes inside of a set of special purpose Cori login nodes. So these are big memory nodes that we deployed with the express purpose of running Jupyter notebooks. So they have, I think, 700 plus gigabytes of memory, lots of processors. But because it's on, it's the equivalent of a login node, you basically also have access to things like the file system and the batch queue, and you have the same Python environment that you're running on the compute side. And so this gets a lot closer to what people actually want. And so that's what we have in production right now. In order to make this work, we had to write a couple of packages to make everything happen smoothly. So we wrote this thing called the GSI Authenticator, which basically lets you log in and grabs, under the covers, it grabs an X509 certificate for you that lets you, manage the GSI SSH connection to the Cori node from within the hub. We also wrote this thing called SSH Spawner, which lets JupyterHub fire up SSH connections and uses the SSH connection to talk to the notebook itself. And it keeps track of the PID there. So this is just sort of a longer version of what I just said. The key thing here is that having this authenticator means that we can, instead of requiring privileged access, all you're doing is getting these certificates and using that to manage it. So no root access is actually required to this setup. And then with the SSH Spawner, you can actually use these X509 certificates to go and talk to the backend service. Now, the SSH Spawner will also let you use SSH keys if that's a preferable way of doing it. So any kind of secure token that you want, you can sort of use with this SSH Spawner. So there's a question here: what is the NERSC deployment doing about internal encryption. So we're just using things out of the box right now. Keep in mind, yeah, so the notebook and the kernel are running on the same node, and so it's less of an issue. But yeah, as soon as we split up the notebook and the kernel, which is something we're looking at doing in the future, that is a problem that we're going to have to solve. But as of now, it's within the same node, and so we're just using the default 0MQ transport. So, but yes, we do recognize that is an open problem. So we also deployed this thing called the Slurm magic, which lets you, basically gives you sort of hooks into the batch queue. So IPython/Jupyter has this notion of a % command. So instead of the native language command, you can type this in, and you can actually use this to submit jobs, to look at the queue, to look at, see what's running. So it's a quick way of just submitting jobs from within the notebook to the Slurm batch system. And we also gave people the ability to write their own custom kernels. So if they didn't want to use our default Anaconda software, they could do their own kernel. So this is mostly just a matter of, using the existing hooks in Jupyter and then documenting things so people can actually use their own kernels. So they just drop a JSON file in their home directory, and that way they can run their own kernels. Moving forward, and since we're running close on time, I'll be a little quicker. But the idea here is that we want to move from this JupyterHub web server that then talks to the login node. We want to also be able to spin up processes on the compute node where you've got the notebook server and the kernel on an individual compute node per user. And then moving forward a little bit further, you want to maybe move towards splitting up the kernel and have that run on compute nodes, and then have the notebook server on its own compute node. We're looking at software-defined networking to make this a little more seamless. So once the hub has everything set up, you can actually advertise an IP out to the world and then directly talk to either the login node or the compute node. So that's sort of an interesting way of doing things and makes things a lot smoother. We've got a LDRD project for doing human-in-the-loop HPC, and this is this idea of having interactive workflows where you have your notebook that can communicate with back-end tasks. And this is sort of just a recap of what I talked about, the idea that you have this Jupyter infrastructure that can spin up notebooks, and you can spin up kernels on the compute node and use software-defined networking to get it to work together. We could have different QoSs and Slurm to be able to support these kinds of things, and then use something like Docker and Shifter to be able to capture environments. So this is all sort of the stuff we're looking at right now and we hope to have in the next year. And yeah, big thanks to folks at Minnesota Supercomputing Center, TAC, SDSC, the Jupyter dev team. We've worked with all of them to put some of this stuff together. So this is by no means our own work. It's sort of a big collaborative effort. So yeah. And finally, yeah, this is kind of a direct quote from a user. They want to be able to do everything in the notebook. It's like the ultimate dream for them. All right, thank you. And
so we do have a few questions for you.
Yep. So I'm looking at the questions here. The one that so there's one about how does data get into the notebook. So the data itself is on the file system, and so you could just load that up directly because the notebook has access to the file system. And then the next thing, does it work with two-factor authentication?
So is anyone else having a hard time hearing? I have lost the speaker.
Oh, sorry, I'm here. Sorry about that.
There you are.
Okay, so the question was two-factor authentication, and the answer is yes. It's completely transparent as far as Jupyter is concerned because Jupyter just the authenticator just falls back on using PAM under the covers, and so that's actually implemented at the OS layer. So the two-factor part is completely transparent from Jupyter's standpoint. And then the other question was, how does data get into the notebook? And the answer there is it's on the file system at NERSC. And so since the Jupyter notebook has direct access to the file system, you can just load it from there into the notebook.
So did you see the one about, are there plans to provide access to Edison Scratch from a Jupyter notebook?
Probably not. We're currently focusing on the Cori file system and the Cori system. There are a couple of, yeah. So I think the short answer is not immediately, but if there's enough people asking for it, we can find a way to make it happen through some sort of. We can mount the Edison file system. We can cross-mount it if we have enough people asking for that. It would still run on the Cori node, but we might be able to cross-mount that file system if there's some demand for that.
All right, I think that we have addressed all of the questions in the Google Doc and the chat box. So, David, do you want to take it from here?
There, maybe.
Hey, David. Oh, I can hear you now. Oh, no.
Thank you to our speakers and also to everyone who participated today. It's your involvement that keeps us going. We'd very much like to get feedback from you. Once again, the link is at the top of the slide. We will make recordings and a copy of the slides available online, so look for some email about that or just go visit either of these links a little bit later on. And then I'd like to mention that the next webinar in the HPC Best Practices series will be on March 21st. The topic is Eclipse for HPC, the Eclipse IDE Integrated Development Environment. Speaker will be Greg Watson from Oak Ridge National Lab. Thank you all very much, and we'll see you next month.